All right, so let's go ahead and take a look at our Chapter 7, Objective 8. So what we're going to be working with is improper integrals. And so this could be a little bit tricky sometimes in like understanding what to do, but actually doing it is not bad. Like if you can integrate a definite integral, then this is not going to be horrible for you. So, but this is a really good lead-in for us for when we get into our Chapter 8. And so like the more you can kind of understand what we're talking about in 7.8, like the better. So the two types of improper integrals that we're going to be working with are if we have an unbounded limit, which is our first case. So we have some sort of infinity, whether it's in both the upper and the lower, hopefully not, or just in the upper or just in the lower. Then we have our first situation, which is when we have an unbounded limit. Okay, so that will be our first one. So this is what we call an improper integral. And we can't just integrate it and like plug in infinity and plug in a. Like that's not something we can do. We have to rewrite it as a limit. So we have to take that infinite value out of the either upper or the lower, and then rewrite it as, the upper limit approaching infinity or the lower limit approaching infinity, or split it into two different functions and then do the same thing again. So this is an essential step. Like we must rewrite as a limit because the first fundamental theorem of calculus does not allow for, that upper limit being infinity or being unbounded. Okay, so we have to rewrite as a limit. I guess I need to include this one as well, but we pray that this one won't come because that's just like a lot of extra work. Not that it's terrible, but we want to definitely avoid that. So what we're looking for, and when we have these limits to infinity, is we're looking to see, does the improper integral converge or does it diverge? Okay, converge or diverge. It converges if we can actually evaluate the limit. So if the limit exists, then it is said to converge. And that means that there is a finite area, even though we have infinite boundaries. So in general, like if I had a function that looked like, y equals x squared, for example, and I want to know what is the area from 0 to infinity, I would not even look for it because it would just be infinite and it would diverge. However, if I had, something like, 1 over x squared, so this is just one side of it, as we're going from 0 to infinity, then, or wherever we're going from, how about 1 to infinity? So I don't have to look at two different places where it's undefined. So 1 over x squared. So we start at 1. I can see that, there's some sort of area right here, but the closer I go or the further out to infinity I go, the negligibleness of, is that a word, of this area, like, that area becomes negligible because it's so tiny, right? And it's approaching 0 because the graph itself is approaching the x-axis. So that area of 0 down here is not adding to the area that you could potentially find at the beginning. So when we go out to infinity, we're checking to see, could we converge? Could we diverge? That's what we're looking for. So diverge would look something, similar to this, where the area just like increases without bound, whereas converge would look something like this, where this area that we're adding to it is near 0, so it's not adding area to this beginning component. Diverge doesn't always mean goes to infinity, though, by the way. It just means it doesn't settle in on a finite value. But most of what we do is going to be, when we say something diverges, it's because it goes to infinity. But it is also, and we'll see this in Chapter 8, it just doesn't settle in on a value. Like it doesn't converge to 5. It maybe goes between 5 and then -5, 5 and then -5. But mostly what we do is we talk about something diverging. At least in this particular objective, that area will go to infinity. Okay, so let's go ahead and see. Okay, well, that was a lot. So how do I do these problems? So let's take a look at how do we do these problems. So the very first thing we need to do is rewrite as a limit when we're working with improper integrals. Like that does have to be your first piece of things. Okay, so when I'm looking at this, I can see that I have this upper limit of infinity. And so I need to make sure that I don't have that written in that fashion, right? So I'm going to say that I'm going to take the limit, and then instead of infinity, I'm going to use the letter B. And I'm going to say as B approaches infinity. And you really can use any letter you want. I'm just using B. Okay. So what I'm trying to investigate and see is, will this converge or will this diverge? So I'm going to go through the process of actually solving this, and then we're going to take a look a little bit at an investigation component to see a little bit more about what we're seeing or what this even means. So then once we rewrite as a limit, then we're going to integrate and then evaluate. So the u here would be negative x, that power here. And so then that du would be negative 1 dx, and then divide by negative 1. So then I will have the limit as b approaches infinity, and then this would be e to the u. And then I'm going to pull that negative out front. And then I'm going to actually integrate this and then put it back into terms of x each time. So instead of changing my limits, I'm just going to integrate. So e to the u is just e to the u, and then replace u with negative x. So I just integrated like what is a pattern and then did the substitution at the same time. And then I'm going to leave the limits as 0 and b. So instead of having to figure out like what would the upper limit and lower limit need to be in order to do a u to u substitution, I just did on my last step, just did straight into a substitution here. So then now we're going to evaluate this at b. And then minus evaluate at 0. So I substituted in b and then 0. And then e to the 0, so this would just be 0, would be 1. So this is just a 1 here. And then e to the negative b is the same as 1 over e to the b. And so as b approaches infinity, that means my denominator is getting large, right? So the denominator is approaching infinity, which will make the whole fraction approach 0, right? So the larger the denominator, the smaller the fraction. And so then my final answer here would just, if I distribute in that negative, so negative, negative 1, so my final answer would be 1. So then therefore, I know that my integral that I started with, that improper integral, converges to 1. So let's make sure like we get like, what is that trying to say? Like, what are we doing there? So I'm going to go into Desmos. So this is like a good way for us, just to kind of see like what's happening here. What are we even looking for? So first I'm going to start with just the equation that I was graphing. So that was y equals e, or not graphing, but integrating. So I'm going to just graph that first. So that first one is e to the negative x. So that's what that one looks like, right? And then what I was trying to do was figure out, well, what is that area between 0 and infinity? So like this like little section, right here going to infinity. So I can see like, when I go out, to the right, like the graph kind of disappears and fades into the x-axis because that area is closing off, right? So supposedly then, like this area right here is 0, from 0 to infinity. So I'm going to do integral over here, so int, and we're going to go from 0, and I'm just going to start out at 10. We're near infinity, whatever, like close enough. So I can see that the area from 0 to 10 is equal to 0.999 repeating, right? So if I were to shrink this just a little bit, so if I were to calculate the area from, oops, let me let go of that. From 0 to 10, they're saying the area is 0.999 repeating. So what if it wasn't 10? What if it was 100? Oh, hey, look. It's 1. And what if it was 1,000? Hey, it's still 1. And 10,000? Hey, it's still 1. And that's because the further out I go, I'm adding area of 0, right? Because the graph closes to the x-axis. Okay, so that's like what we're looking for. And so that's, there's like kind of a visual for that. All right, so let's go back into the next problem. So for this one right here, so again, if I go through this graph right here, and so let's rewrite it. So I was going to go ahead and graph it so we can take a look at that. So let's do a rewrite first. So we have 0, and then negative infinity is the improper component. So I'm going to switch that. Actually, let's do that as letter A. Not that it matters, but I'll stay consistent here. So we'll go from A being our lower limit. And then as A approaches negative infinity. Okay, so again, I'm going to graph it just so that we can get a visual on what we're trying to investigate and find. So let's go ahead and do that. So what was the equation? So it was x, and then e to the negative 2x dx. And then let me close this off. So this time, what we were looking at for this particular one is we were actually finding the value from negative infinity to 0, right? So if I'm looking for the area from negative infinity to 0, that's all of this right here. And do you see how the branch of this graph does not close to the x-axis? So if I look at that integral, so we were going from negative infinity to 0. So I'm going to just start with negative 10 to 0, because 10 is super close, right? Like that's right there at negative infinity. Okay, so I can see that this area is negative 2.3 times 10 to the 9th, right? So what is that, like 2 billion? And I'm only at negative 10. So if I went to negative 100, let's see if we can break Desmos. So negative 3 times 10. So I, honestly, I don't even know that I want to do this problem because I can see graphically that it's going to diverge, right? So why go through that nonsense, right? Or not nonsense. Calculus is not nonsense. Why would I say something like that? So I don't know. What did the graph look like? It looked like it had like a little hiccup there, and then it shot down. And so we're looking for this area here, which diverges. So we're just going to say that this diverges because the area increases without bound, right? In a negative direction. But if you want a little challenge for yourself, you should go ahead and actually integrate that. And then just as a reminder, this would be an integration by parts. And I know that because I have my polynomial in transcendental. So if I let u equal x and then du be 1 dx, and then the dv piece would be e to the negative 2x dx, and then v would be negative 1/2 e to the negative 2x because of the u du right here. And so I'm not going to do this whole problem for you, but I feel like this would be a good one for you to practice on your own. That's a negative there. And so that would be, oops, let me go back. So this would be, what would that be? U times V. So U times V from A to 0. And then minus the integral of V du. So let's pull out that negative 1/2. Let me double bracketed that. Okay. So, but maybe go through and try that and see if and hopefully you get negative infinity when you do that. Okay. All right. So with that said, let's look at the second case about, what makes something be an improper integral, right? So right at the beginning there, we talked about there was 2 particular types of improper integral. So the second type is when it's not going to infinity, but going to a point of discontinuity. So the point of discontinuity, may be the right side of the limit, maybe it's the left side, or maybe it's just smack dab in the middle. So meaning that, that whatever this upper limit is here, for example, it's not defined for the function, not in the domain of the function. These are the worst case situation because they're so sneaky. Like you're just like, oh, look, it just looks normal and I'll just go and integrate. And then you end up actually losing a fair amount of credit because you never took note of the fact that, hey, I can't have 8b in this denominator because then I would be dividing by 0. So this is a second situation for improper integrals, is that when you have a point that's not in the domain of your function, is either on the edge of your limits or somewhere embedded in the middle, which that's even worse. So that means from here on, BC people, you can't just integrate a definite integral. You need to check to make sure that it's not improper because the steps are going to be exactly the same. Okay, so we're going to solve this just like we did with infinite limits, but we have number values to contend with. So our first step is still going to be to, rewrite as a limit, in terms of the solving component, but really our first step from here on out is to make sure that your function is defined for whatever your limit values, okay? So essentially check your domain and make sure that you don't have an improper integral. Okay, so we're learning improper integrals, so these will be improper. So we're going to check it. So I know right here, right off the bat, x cannot equal 8, but unfortunately it is my upper limit. So then once we see that, we're going to rewrite as a limit, just like we did on the previous problems. And then once we do that, we can investigate like we did in the Desmos, but we're just going to go ahead and just solve each of these. But I would highly recommend you graph and check it to see, first of all, if your answer is correct, right? So you could definitely do that. So we're going to rewrite as a limit, and then we're going to, solve the integral and evaluate. Okay, so then we'll find that integral, whatever that happens to be, and evaluate. So really the same steps as the front side, it's just this one that we have that added piece about that we have to take into account. Okay, so I'm going to rewrite this as a limit. So we have my upper limit is a part that's undefined. So we're going to let b approach 8. And then I'm going to bring this up to the top to make that easier to integrate. And so I would let u equal 8 minus x, and then that derivative would be negative 1 dx, and then I'll divide that negative 1 over. So the negative 1 I divided out. So I'm going to do the same thing I did. I'm going to integrate this and then substitute in that respect to x component so I don't have to worry about trying to find the new limits. So I would have negative 1 from here and then add 1 to the power, so that would be 2/3, and then divide by 2/3 is the same as multiply by 3/2, and then whatever my limits are here, but I'm going to go ahead, looks like 13, but I'm going to go ahead and replace my u term with my x values. So what I'm doing here essentially is just saving myself a little bit of trouble of having to find new limits, and I'm going to stick with my limits in terms of x. Oops. So the u I just swapped out for that, and then again I'm going from 0 to b. I just realized I wrote infinity all the way down here. Let me fix that. So how about it doesn't go to infinity, it goes to 8. So B is, yes, approaching 8. 8 looks too much like infinity, and so I had that on the brain there. Okay. So the limit as b approaches 8, and then now substitute in b and 0. So I have negative 3/2, and then I would have 8 minus b to the 2/3, and then minus 8 minus 0 to the 2/3. There we go. So then as b approaches 8, I would have 8 minus 8, which is 0. So this will approach 0. And so then what would that be? Oh, I guess I don't have any more limit. So let me erase that. I got all, there we go. So do some mental math here. So 8 minus 0. So what is that? Negative 3/2. And then that would be the cube root of 8. And then squared. And then, oh wait, I have a double negative. So that'll be plus. So I distributed that in. So what is that? Cube root of 8 is 2. Squared is 4. 12 divided by 2 is 6. So a value of 6. Yeah, there we go. And again, so I would highly recommend that you try to, do this in Desmos. And so just to kind of always check your answers, right? So you don't really need to graph it. Like you can graph it if you want to, but you don't. But you can certainly in here. So what was our equation? So let me just do that. So you can see what I'm saying about that. So we went from 0, and then this was 1 over, oops, what the heck? What the heck? 1 over the square root. No, it wasn't. It was the cube root. 1 over the cube root of 8 minus x. And then we are going from 0 to 8. So if I put in 8, I get that 5.9 repeating, which is 6, right? Because you can't actually evaluate at 8, but Desmos knows that. And so it's probably using some sort of fabulous programming. All right, so let's go ahead, and I think we have just one more here, so let's do this one. And this one I won't graph in Desmos, you can do that. So again, I check my domain. I know if I look at here, x cannot equal 0, because then I would be dividing by 0. And so this is an improper component, so I'm going to rewrite that as a limit. So the limit, gracious, I'm not on my A game. On my B minus game right now. Okay, so the limit as A approaches 0, not infinity, from A to 2, and then I'm going to rewrite that as x to the negative 3 dx. Okay, so then from here, I'm going to just, this is nice because that's just power rule, so let's go ahead and do that. Nothing fancy here. So add 1 to the power and then divide, and then we're going from A to 2. I'm going to go ahead and actually rewrite that because I can see where I could potentially make a mistake. So that would be 1 over and then negative 2x squared. There we go. That looks more like something I can manage. And then I'm going to go ahead and substitute in the 2 and then the A as well. So if I put in 2, I'll get 2 squared is 4, so that would be negative 8, and then minus 1 over negative 2a squared. And then if a is approaching 0, so that means my denominator is getting small, right, approaching 0. And so the smaller the denominator, the larger the fraction, and so that means this whole thing will go to infinity. And so then my limit does not exist, right? Does not exist because it's unbounded. And so then, therefore, the improper integral of 0 to 2, or from 0 to 2 of 1 over x cubed dx would diverge. And so if I graphed it in my calculator or Desmos, I would see that it's going to be shooting to infinity.